So here we have a problem about legless firing an arrow horizontally with a velocity of 45 meters per second from a height of 1.7 meters above the ground. So notice we have a couple of variables given in the problem, but there's actually more that we know in this problem. But first of all, what I want you guys to focus on is these three parts. We're going to do C and D tomorrow. Today I want you to solve for final horizontal velocity, hang time, and range. And we've already defined what range is and what hang time is. And we know a little bit about horizontal velocity. Okay, so first thing you want to do is sketch a diagram. So notice my diagram here is pretty simple. There's no need to sketch a diagram of legless, but if you want to, you could. You don't need to draw the bow, but you could if you wanted. Okay, but this arrow, the big blue arrow in the picture, represents the velocity in the problem. Okay, so let's go ahead and label everything that we know in this problem. Well, we know that this arrow represents initial velocity, and the initial velocity equals the initial horizontal velocity, which we know equals 45 meters per second. Now, initial velocity is equal to the initial horizontal velocity because there is no vertical velocity. We know that velocity is going to be the sum of its components, the horizontal and the vertical. And in this case, there's only horizontal component. So that takes us to the vertical component. What is the vertical component? It is 0. So V naught is the sum of V naught x and V naught y. It's a resultant, like we learned in vectors earlier. Now, we also know that this is the horizontal displacement, and this is the vertical displacement given with a y. So that leaves us with three variables, and they're going to go over here. This represents the total final velocity. This is the horizontal final velocity and the vertical final velocity. So we can put those over here like this. Final velocity, final horizontal, and final vertical. Now we're going to actually solve for this triangle over here in part C and D tomorrow. So all we're going to do right now is focus on A, B, and C. And notice we already solved for A. Okay, on part A, right here, part A, V naught x always equals Vx. Okay? So the horizontal velocity remains unchanged. Okay, so that's easy. Just a concept you need to remember. All right, let's make ourselves a little bit of room, and we're going to work on part 2, the hang time. All right, let's get this out of the way. All right, we're going to leave that as a reference. And then what we're going to do is we're going to divide or organize all our information into two parts, like we did when we were doing vectors earlier. We want to look at all the variables related to the horizontal components and all the variables related to the vertical components. So, what exactly is involved horizontally? Well, horizontally, of course, we have x. We don't know x yet. We have V naught x, which is 45 meters per second. And the one variable that is the same for both horizontal and vertical is going to be time. Okay? The time is going to be the common factor between horizontal and vertical. That's the only variable that's shared between the two. Now, here's a new equation that I need to make you aware of. We already know that V is x over t. And if we're talking about horizontal velocity, we put V sub x there. So therefore, x equals Vxt. And this is the equation to solve for range. Okay? So that's the only equation that's used here, the range equation. Okay? Range equation. Actually, let me write the equation. That's going to be x equals dxt. This equation is always going to be used in the horizontal. What's going to be used in the vertical? Okay, that's going to be 4 kinematics. 4 kinematic equations will be used on the right side of the T chart that we have. It's always going to be one of the 4 kinematics, or maybe more than one of the 4 kinematics. But on the left side, on the horizontal side, it's always going to be the range equation, okay? All right, so make a note of that. Now, let's go over here and look at what we're given on the vertical side. Well, we're, of course, y, and y is 1.7, right? No. Legolas's arrow starts at a position where he's holding the bow, and then it falls negative 1.7 meters to the ground. So because it goes below the initial value, then that's going to be negative. What else is given? Well, we know g is always negative 9.8 meters per second squared. And we also know that the initial vertical velocity is 0. The arrow has to start from somewhere. So even though he shot it with a great velocity of 45 meters per second horizontally, vertically, it started at 0. It had to start from somewhere when it began to fall, and it started from 0 in this case. Now we have 3 out of 4 variables. We're looking for, well, ultimately what we want to do is find hang time. So we're looking for t here. And these two t's are going to be the same. These two t's are going to be the same. So we can use those interchangeably. So once we've solved for time on the vertical side, we can bring that over to the horizontal side and solve for the horizontal displacement. So let me go ahead and take this, shrink it down so we can use it as a resource, as a reference. And we're going to put it over here with the sketch. Okay? All right. Now, let's solve for t. Well, if we've got these 3 variables and we're looking for t, there's no mention of final velocity. There's no final velocity in these particular lists of variables. So what we're going to do is pick the equation that does not have final velocity in it, which is y equals v not yt plus 1/2 gt squared. Notice that since v naught y is 0, that is going to cancel out. That's going to leave us with y equals 1/2 gt squared. Now we're looking for t, so we're going to divide both sides by 1/2 g. Okay? And that's going to leave us with t squared equals y over 1/2 g. And we can also write that as the square root of 2y over g. If we plug that in, we get 2 times negative 1.7 meters over negative 9.8 meters per second squared. Okay? And we work that out. 2 times 1.7 divided by 9.8. And second square root of the answer, we get 0.589 seconds. And in terms of sig figs, our answer is going to be 0.59 seconds. Okay? Now this goes here, and it goes here. So the time is the same for both. It's very important. Okay? All right. Let me now do this. We're almost done. Now all we want to do is solve for the range. So I'm going to group all this together. Shrink it down one more time. Okay. Bring it over here. Now what we want to do is we want to take the t and the x and v naught x, and we want to solve for x over here. Okay? So what we're going to do is we know that x equals dxt. So x equals 45 meters per second over time, which is 0.59. But let's use our original number of 0.589. Let's don't round yet. Since we're solving for a different variable, let's wait and round that last. Okay, so we plug that in, and we get 26.5. 26.5. So we could round that. That's pretty close. Technically, I think we'd probably round that down. If it was 26.55, we'd round it up. When it's borderline like that, I'm not going to be too picky about it. I'll let you go in either direction. But that's where I'm going to settle right there, 26 meters. So what we've done now is we've solved for the hang time here. We've solved for the range here. And these are going to be the two components that are important for the horizontal velocity lab, projectile lab that you guys are doing.